I'm Weicheng. I'm from Hogan Mills Group at UC Berkeley. I'm very glad to be here. I have learned a lot. Today I'm going to tell you about measuring the Fourier constant with atom interferometry. So this project has a history of more than 15 years. It used to be my advisor Hogan Mills postdoc project at Stanford. And we finished the project last year and had the result published. And since then, we have some updates, and so today I'm going to give a review of the experiment and also talk about some of the planned upgrades. So the main technique used in our experiment is atom interferometry. And so what is an atom interferometer? I'd like to introduce atom interferometer with an analogy on laser interferometer, like LIGO. So for a laser interferometer, the coherent source is a laser, and then you have like a beam splitter and a mirror to split the laser, and then use a beam splitter again to combine the laser beams and have a detector here to detect the intensity. So the idea is the intensity here can be related to the differential phase the laser beam accumulated between different passes. And for atom interferometers, it's very similar. The difference is here our coherent source is a matter wave, usually in the form of ultra-cold atoms, and we use diffracting gradients, usually it's like to counter-propagating waves to do the splitting, redirecting, and combine the matter waves, and we detect the intensity, so basically the atom population here. And then from this intensity, we can get information of the differential phase the atoms acquire between different passes. So why do we want to do that? Because atoms are sensitive to gravity, and so using atom interferometers, we can measure gravity very accurately. And atoms can also be kicked by photons. Using the photon recoils, we can measure things like the Fourier constant. So I'd like to start with two fun projects happened recently in our group. The first one, I think Igor has talked about. So it's the cavity. It's the atom interferometer in an optical cavity. So since 1991, people started building atom interferometers. People are trying to make taller and taller atom interferometers because then the atom have longer freefall time. The atoms can interact with gravity for a longer time. So here, when it's first built, the freefall time is only 10 milliseconds. And for the 10-meter atomic fountain in Stanford, they achieve a freefall time of 2 seconds. And then there's a proposed 100-meter tall gravitational wave detector, which will have a freefall time less than 10 seconds. And in our group, we developed a new way to increase this interaction time between atoms and gravity. So basically, we hold the atoms into an optical lattice created by the mode of an optical cavity. And this cavity will also work as a mode filter, so it can help overcome some defacing sources. And by doing that, we achieve more than 20 seconds coherent time. So if you think about 20 milliseconds, it's not that long, but if you want to get 20 seconds freefall time in an atomic fountain, the fountain needs to be like 500 meters tall. Yeah, so that's why it's fancy. Another experiment I'd like to talk about is a more practical usage of atom interferometer. So here, what you see here is a mobile atom interferometer. It has only one dot laser and a pyramid mirror, so it's very compact and stable. Here, what you see here is a continuous measurement of gravity in the lab for 14 days, and you can see the gravity you can measure as different day by day. That's because of the tidal effect. And if you look more carefully, then you can see these high order effects. That's because it's in Berkeley, so the water level in the Bay Area changes, and then that will affect the gravity in our lab. And during the data taken time, we also detect two earthquakes in different places of the Earth. I think one is happened in Brazil, and one has happened in Indonesia. So that's and also it's designed to be mobile. So you can see the size of the interferometer. It can fit in a truck. So we put the atom interferometer in a truck and then drive the truck along the Berkeley Hill to do a gravity survey. So this is the path of the truck. And so we park the truck at different places and tune the apparatus for 10 seconds and measure gravity in that place for 2 minutes. And then we got this plot. It's a gravity versus elevation, and you can see as a relationship between elevation and gravity. And from this relationship, we can determine the density of the rock in the Berkeley Hill area. Yeah.
How was the elevation measured?
What?
How was the elevation measured?
I think it's a read from Google Maps.
Yeah. Okay.
Yeah, but this is for the first time we can do a real atomic physics experiment outside the lab. Yeah, but now I want to switch gear. So I want to tell you about my experiment measuring the Fangio constant. So Fangio constant, why Fangio constant is interesting? Fangio constant is used in different branches of physics and can be measured by different ways. In the old days, it is measured by the quantum Hall effect or the helium Fangio constant. But nowadays, the most accurate determination of the Fangio constant comes from two kinds of experiments. The first one is the green points here. These are measured using atom interferometry, and so they use atom interferometers to measure the recoil frequency of a neutral atom and then determine the alpha. Another kind of experiment is these red points. And these are measuring the electron gyromagnetic anomaly, G-2, and then you can derive alpha from G-2 using theory. So here now let's zoom in on these 3 points. So in this inset is these 3 most accurate measurements. So before our measurement, the most precise measurement comes from LKB in France. They use atom interferometer and they use rubidium atoms. So, and they achieved an accuracy about 0.6 per billion. And then Professor Jerry Gabriel from Harvard here measured the G-2 in a penny trap, and they can derive alpha from G-2, and the accuracy here is 0.24 per billion. And last year, our result was published. So we use atom interferometers and we use cesium atoms, and our accuracy is 0.20 per billion. So our measurement is so far the most accurate measurement of alpha, but really these 2 experiments are almost the same. So that's a very unique situation in physics now. Let me show you this one. So on the left is our Fangio constant measurement. And using atom interferometers, and on the right, that's Professor Jerry Gabriel measuring G-2 using a penny trap. So these are two of the most accurate atomic physics measurements in the world. And actually, there's there is a standard model linking these 2 experiments together. So here, G-2 can be written as a function of the Fangio constant. And these coefficients AN come from QED, quantum electrodynamic theory, and we also need to include theories like muon and tau and weak and strong interactions. So in order for this equation to check out, most parts of the standard model needs to check out. But what if this equation doesn't hold? Then what if this equation doesn't hold? Then that's an implication for beyond standard model physics. Yeah, so that's the idea. Okay, so how do we measure the Fangio constant using atom interferometers? So here we learned this equation maybe from undergraduate studies. Alpha squared over 2, that's the ratio of the bonding energy in hydrogen and the rest energy of an electron. And we can rewrite this equation like this. So now alpha can be written as a product of different terms. This Rydberg constant this readable constant has been measured using hydrogen spectroscopy to 7 per bajillion level. And the mass of an electron and the mass of the cesium atom have also been measured in penny traps to very high accuracy. The overall uncertainty of alpha is limited by h over m. So that's what we measure. We use atom interferometers to measure h over m to 0.3 per billion. This will give us an overall uncertainty in alpha about 0.20 per billion. And so I also want to point out that in the newly published SI unit, this h, the Planck constant, is now a real constant, so there's no uncertainty with it. So what we are measuring is the, you can think that what we are measuring is the mass of a cesium atom. Yeah, so how do we use atom interferometer to measure h over m? So let's imagine a scenario that we have an atom, there's Bragg here, and then we apply a resonant photon to interact with atoms. So the atom will absorb the photon and get a small velocity. That's a recoil velocity. There's a kinetic energy associated with this recoil velocity. That's 1/2 mvr squared, and we can define a recoil frequency with respect to this energy, the h bar omega r. That's a recoil frequency. And in the definition of the recoil frequency, h bar k squared over 2m, you see this h over m here. But we also, then you will also see this k, that's the wave number of the laser beam. So the wave number of the laser beam can be measured by a frequency comb. So you use a frequency comb, so that's no problem. But how do we measure this recoil frequency? Yeah. So you can think that once the atom gets kicked by a little bit, then the resonant frequency will be changed by a little bit due to the Doppler effect. But the Doppler effect is about 2 kilohertz, and we want an accuracy of 10 to minus 10. And here, this the cesium D2 transition has a frequency of 350 terahertz. So it's like we want to pinpoint resonance 0.2 microhertz to 350 terahertz, or we want to achieve accuracy of 6 times 10 to minus 20. So that's already beyond the current most advanced optical clock. And that's why we need an atom interferometer to measure this recoil frequency. Here is the geometry of the atom interferometer we used in our experiment. And each dashed line represents a pair of counter-propagating beams that will drive the atom into different momentum states, so they work as beam splitters. And the solid line here, these are the trajectories of atoms. One thing you would notice here, the upper arm and the lower arm are not symmetric. The upper arm always moves faster than the lower arm. And that's why when we detect the phase here, this momentum difference between the two arms will enter into the final phase, and that's related to the recoil frequency. So here is a formula for about the phase we can detect using this geometry. Omega r is the recoil frequency we want to measure through this interferometer, and t is the power separation time here. Basically, increasing t will increase the space-time area enclosed in this interferometer. Thus, increase the sensitivity of the interferometer. Yeah, so that's the chain of the measurement. We measure omega r through the interferometer, use a frequency comb to measure k, and then we can get h over m, and therefore determine alpha. Okay, but one problem here you can see is our atom interferometer is also sensitive to gravity, G, which is not what we want. So we develop many techniques to suppress these unwanted effects. The first thing I want to talk about is the simultaneous conjugate Ramsey body interferometer. So basically, we have two Ramsey body interferometers. The upper one is an upside-down version of the lower one, and the gravity is going to have the same effect on these two interferometers. And then we take the differential phase between this interferometer and this interferometer to cancel the effect of G. Then how do we measure how do we cancel this G? We have, because our interferometer is so sensitive, it's sensitive to G and also vibration, then if you plot the interference fringe from either of these, any of the interferometers here, then what you're going to see is basically random jumps. It's not a nice sine wave. But if we plot the interference fringe from the upper interferometer parametrically against the interference from the low interferometer, like this, and then we can trace out an ellipse. Vibration will walk our data points around this ellipse, but the shape of this ellipse, it's like a circle, a line, is determined by this differential phase between these two interferometers. That's how we resolve the differential phase. And we also use many different ways to increase the sensitivity. For example, this multi-photon Bragg diffraction. So in an atom interferometer experiment, there are two kinds of mostly widely used beam split techniques. One is the Raman transition, and one is the Bragg diffraction. For Raman transition is easy to understand. Like you have a pair of counter-propagating pulses, and that will drive the drives the electron from one state to a different electronic state, and at the same time the atom will get 2 photon momentum kick. But for Bragg diffraction, it's a multi-photon process. So for example, we use 5th order Bragg diffraction. So every time the atoms will absorb 5 photons and emit 5 photons at the same time, then our total phase scales with n squared. So using n equals 5, we can increase the total phase by a factor of 25. Another advantage of Bragg diffraction is because the atom stays in the same electronic state all the time, so it's less sensitive to like a magnetic field and electric field. Here is a visualization of the Bragg diffraction process. So we solve the Schrödinger equation about Bragg diffraction numerically and then plot the amplitude of the wave function. So you can see that once we apply the Bragg pulse, the wave packets of the atom split into 2. Okay, and the third technique we used to increase our sensitivity is the Bragg oscillations. So basically, between the second and third between the second and third beam splitter pulse, we load the atoms into an optical cavity, and then we start trip the frequency of this. Into an optical lattice, and then we start trip the frequency of the optical lattice. So the atoms inside the lattice will start moving in the opposite directions. So this will further increase the spatial separation between the upper interferometer and the low interferometer, and our final phase is like this. Here, the capital N is the photon momentum the atom can get from this Bragg oscillation process. If we use n equals 125, then you can see we increase the total phi by another factor like 20. Yeah. Okay, so here is an overview of our setup. We have a mod to capture the atoms from the vapor, and then we launch the atoms upward, so then we can have a longer free fall time to increase the sensitivity. And once the atoms enters this magnetic shield region, we apply the Bragg and Bragg oscillation pulse to interact with the atoms. And atoms will be split into different wave packets. Once the wave packets goes through this detection region, we apply a resonant beam to capture the fluorescence. So that's our final signal. I'm showing some figures about the experiment here. So at least 2 postdocs and 5 graduate students have worked on this experiment. But now we are going to move, so these tables will be amputated very soon, maybe in the next 2 months. Okay, and here I'm showing some data we used to calculate alpha. So our statistical sensitivity is about 0.24 per billion in 24 hours. So actually, we can get this number in less than 2 days, but we took a lot of redundant data to make sure there are no unknown systematic facts. So for example, we vary the Bragg oscillation order, we vary the positive separation time t, and in the end, we have an 0.16 per billion statistical uncertainty. And the data taken campaign took about 7 months. We also adopted a blind analysis protocol. So how we did that? Professor Rana Adhikari from Caltech, he added a random number into our wave frequency. So when we were taking data and checking the systematic facts, we use that wave frequency to calculate alpha. So we don't know where the alpha lies in this band. And after we are confident about our result, Rana would give us this random number, and then we will review our result and submit the result without changing it. Yeah. So now let's look at these measurements again. So these are the 3 most accurate measurements. Some interesting happening here. First, you can see that our work agrees very well with the rubidium measurement in LKB. That's a good thing because they are quite similar. But you can see here there's a slight difference between our work and the Harvard G-2 measurement. So what does this difference mean? Now, if we use our alpha measurement as an input to theoretically predict this electron gyromagnetic anomaly, we can and then compare to the experimentally measured one, we have this difference, and it's about 2.5 sigma tension. So 2.5 sigma tension is not large enough that we can claim we discovered a new physics, but it's not small. So we want to understand what's going on. So what has caused this tension? The first thing came into our mind is the famous muon G-2 anomaly. We know that there's a persistent 3.7 sigma discrepancy in the muon G-2 measurement, and dark photon has been expected to be an explanation for this discrepancy. So can dark photon also explain our electron G-2 anomaly? Actually not, because if dark photon is a reason, then it will cause a positive shift of this electron gyromagnetic anomaly. But here we observe a negative one. So actually our result will constrain the dark photon instead of prove it. Here is the parameter space of dark photon. This band is where the dark photon can explain the muon G-2 anomaly. And actually, before our measurement, the measurement from LKB, they are already contradict to this dark photon explanation and can rule out dark photon at 99.5% confidence level. With the improved measurement from our group, we can now rule out even more spaces. Yeah. And I also want to point out that dark photon are also studied by a lot of particle physics research in the world. So there are other exclusion plots available for this dark photon. Now, dark photon doesn't work for the 2 anomalies. Is there any theory can explain both of the anomalies at the same time? We found this figure online. It's very interesting. So the y-axis is the muon G-2 anomaly, and the x-axis is electron G-2 anomaly. And according to the standard model, both of the anomalies should be 0, but overall there's already more than 4 sigma away from the standard model prediction. So 4 sigma is something we need to think very carefully. Since our paper published, theorists have been working very hard to try to explain why there's a 4 sigma away from the standard deviation. I gave 2 examples here, but I believe there's going to be more theoretical work associated with the deviation. But in terms of experiments, I think what we can do is to keep pushing the accuracy. So maybe one day this 4 sigma deviation will be resolved, or maybe we can confirm there's really 4 sigma deviation. So how do we increase the accuracy? I'm showing the systematic errors, a table of systematic errors we checked before for our measurement. You can see there are some terms are very large, and some terms are new, which haven't been thought about before our measurements. The good thing is the big systematic errors are not new, and the new systematic errors are not big. So I'm not going to go through all of them. I will only talk about 2 of them, and to explain how we are going to improve the systematics. The first thing I want to talk about is the non-Gaussian waveform. So we know that a Gaussian beam the wavefront of a Gaussian beam has some curvature, so the wave vector at different places are slightly different. We need to correct for that systematic effect in our experiment. And what's worse, usually a Gaussian beam in a lab comes from a fiber, and those fibers have a step mode, like a refractive index. That means the real waveform is only Gaussian near the center of the beam. 2 beam widths away, it's more like Lorentzian, and then this large tail will be reflected by the vacuum chamber and interact with our atoms. And what's worse, so here is a real CCD image of our laser beam, and you can see it's kind of messy. So there are a lot of high frequency noises caused by the dust on the mirrors and the view ports. We used to believe that this high frequency noise will average out by the atoms, so will not cause an overall shift. But it turns out that this high frequency small scale intensity variations will lead to a big change in the GUI phase, because at high intensity regions, the atoms is more likely to be kicked by the atoms, and low intensity regions, the atoms has a lower probability to interact with the laser beam. So the overall effect is not 0. And this has been a big problem for LKB, who did the rubidium alpha measurement. So that can cause more than 10 per billion shift for their result. For our experiment, we use a 3D multi-color simulation to take care of this effect, and we bound this effect to less than 0.1 per billion. Yeah. Now, how do we solve these problems? One straightforward way is to increase the dimension of the laser beam. As we increase the dimension of the laser beam, then the atoms will see a more uniform wavefronts. But the problem is, to use a big laser beam, we need high power lasers. So here is a high power pulsed laser system, and we have so basically we have 3 amplifiers to amplify the 1064 nanometer laser from a YAG laser, and then have an LBOS HG to double the frequency to the green light. And then we use an OPA to change the frequency from 532 to 852. So part of the experiment, part of the setup here has already been demonstrated by Professor David DeMille from Yale, and we are now working on this part. Yes, because there's a high power green light, so that's why we call it Death Star. And I want to mention that the state-of-the-art M² laser has a power only about 5 watts, and we are expecting that getting hundreds of watts peak power from this system. We already have some green light here. It's only a few milliwatt, but I think we are getting close. Yeah, but to house a large laser beam, we also need a big vacuum chamber. That's why we are redesigning the vacuum system in our experiment. So I'm going to show so this is a design of the vacuum chamber. It is 4 meters tall, 6-inch diameter, and weighs more than 5,000 pounds. And the whole chamber gonna be inside a magnetic and acoustic shielded room. And there are also vibration isolation stages to mount this giant chamber. Yeah, this chamber will arrive in the end of October, but we already have the magnetic shield. The magnetic shield will be installed inside the vacuum chamber, and you can see how big this magnetic shield is. Here is my colleague Zach Pagel with the magnetic shield, and here is my lab mate trying to move the magnetic shield into a different room, so it's not going to block the hallway of the building. And this is what it looks like inside the vacuum chamber. It's gonna have complex structures to capture the stray light, because we don't want the laser beam be reflected back from the vacuum chamber. And here is my advisor, Hogan Mueller. He is sitting on this optical table, and this hole is about 1 meter in diameter. This is a huge project, so we are collaborating with Lawrence Berkeley National Lab. Scientists and engineers in LBN are helping us designing high-power fibers, high-quality city imaging, and improve the Monte Carlo simulations, and also about mechanical engineering, for example, how to stabilize such a big chunk of metal. Okay. The second systematic effect I want to talk about is gravity gradient. So as I said, we have simultaneous conjugate interferometers. We can cancel gravity effect, but the two interferometers are still at different heights. So higher order gravity effects still enters into our systematic effects. What's worse, the phase from gravity gradient scales with t cubic. That means when we increase the power separation time t to increase sensitivity, the effect from gravity gradient will also be more pronounced. So we need to think about a way to get rid of this phase. For the previous measurement, we configure our interferometer into a gradiometer, so it has two Mach-Zehnder interferometers. And each one will measure gravity at different heights, and then we take the difference divided by the base length of the baseline. We can get this the gravity gradient in situ. But you can see that because this gravity gradient is measured experimentally, there is an associated uncertainty on gamma, and this will ultimately limit our accuracy. So to take care of these systematic effects, we now demonstrate a new interferometer configuration. So basically, we now have two simultaneous conjugate interferometers, and they are offset by a vertical distance. So that's why we call it offset simultaneous conjugate interferometers. This geometry has 4 output channels, and different combinations of these output channels will give us the different information we want. For alpha measurement, let's look at the channel B and the channel C. So channel B and channel C can be at the same average height. Then we by measuring the differential phase from B and C, we can cancel gravity gradient effect. And here the some fluorescent trace and the ellipse we can read out from this geometry. Okay, now let's look at the table again. So here are the systematic effects for the previous measurement. For these terms, the GUI phase, the wavefront curvatures, and so on, they are going to be taken care of by the large and clean laser beam. For the acceleration gradient, it is going to be taken care of by the offset simultaneous conjugate interferometer. And the other terms, we can do a better measurement or characterization to get rid of them. So now we are ready for 1 order of magnitude improvement. What's better? So the AMO community, we just learned that LKB, the LKB group, who did this experiment, they have already achieved good statistical sensitivity, but they are still bothered by some systematic effects, and we expect them to update this measurement very soon. And Professor Klaus Bloom is going to do an improved measurement of cesium mass, because when we calculate alpha, the uncertainty on cesium will also enter into the final uncertainty of alpha. And Professor Gerald Gabriel, now as in Northwestern, he proposed a 10 times better G-2 measurement. With all these efforts, so this is what we are looking forward to. So here is the actual G-2 factored into different contributions, like different order of QED contribution and muon contribution, Thorne contribution, strong and weak interaction contributions. Here is what we are at right now. That's the G-2 measurement. That's the hour measurement. The comparison now reaches the accuracy of the fifth order QED contribution and the hadronic contribution. With 10 times better G-2 and alpha measurement, we are going to see the uncertainty of this fifth order QED contribution, and we are also going to be able to measure the weak contribution for the first time. Yeah, so I'm going to so here's the conclusion of the talk. So we achieved 0.20 per billion last year, and we are moving to the next generation of measurement. As my advisor Holger Miller said, we are not inventing the wheel, because last measurement took more than 15 years, and we expect the next generation experiment to happen in 3 and 4 years, because we are going to recycle some techniques. And we are going to have an improved laser beam. We are going to have a high power pulsed laser system, and we are going to have a new vacuum chamber. And also we have excellent engineers and scientists from LB and L to help us. And that we have the Oski geometry to cancel the gravity gradient. And here is the group members in our lab. That's me and Zach here are the 2 graduate students working on this project. And we have LB and L specialists working on the project too. And we have some visiting students and undergraduate students. Dr. Richard Parker used to be the postdoc of this project. He left several months ago, and that's him. The thing he is holding is a whiskey. That's a gift that's the present we give to him. And if you look closely, this whiskey has 137 proof. So that's we checked several stores to find this thing. This whiskey is more than $200. So but anyway, that's no point. So it's alpha whiskey. Yeah. With that, I thank you for your attention.
Thanks for this beautiful summary. Do you have questions?
So when you are cancelling the gravity properties, right?
Yeah.
So you are doing it in kind of vertical direction.
Yes.
Sure. But due to nearby objects, there could also be gravity gradient noise in the other direction.
Yes, that's a very good question. So let me show you the design of the vacuum chamber. We have already thought about the problem. So that's why you see here this vacuum chamber. The real interference process going to happen in this tube, and you see it's far away from the optical table or the other objects. Yeah, that's how we designed it. So cooling is going to be happening here, atom fly to here, and then we do the real science to prevent all the high order gravity effects. Cool.
So it's very seismic, not below.
Yeah. Yeah.
So as these become much more sensitive and you start to see the theory uncertainties, is there any prospect for improving the hadronic contribution theory uncertainty? Is this a measurement or is it calculated?
The answer is I don't know. So the hadronic contribution here. So I would say we are already able to detect the hadronic contribution here.
But the uncertainty on it?
The uncertainty, then we need to wait for the next generation of the measurement.
But can the theorists actually improve that calculus? Sometimes these hadronic things are measured and
Yes,
they only do
yeah.
as well as the measurement.
Yeah, but so far I haven't seen any update for the hadronic measurement. Hopefully our measurement can be a motivation for the service to work on it.
similar question, but about the tau electron.
Mm.
I'm just curious, are you kind of starting to touch upon that? I'm curious if there's some physics you can probe in terms of, I don't know, some of these high energy mixing waves or something that you would be able to sense.
Yes, for sure. I think if theorists would work on this, like the conversion from muon and Thom, but as experimental physicists, we leave the job to the theorists.
Any comments on that? But let's say you send alpha what it is, and you don't want to measure that. Like, can you be sensitive to some interesting physics in there, which is some kind of very strong 3D.
Well, yeah, tau is all of it. So there seems like there's a lot of interesting physics
Yeah.
that have to enter that theories don't really know.
Yeah, so what we got is this number, and we try to understand, we compare to the theoretical prediction of the GMAT2. And in terms of the how we factor GMAT2 from different contributions, I've never thought carefully about that, but I think you're right, and we would see interesting physics as this, for this contribution.
If there are no more questions, then thanks a lot one more time. And say thanks a lot to everyone. This is the ones who stayed now in the end. We got diluted a little bit. But so, just from a personal point of view, this was a great tour de force. I'm very happy that everyone we invited could come. And I was a little bit reminded on a visit I had in Tech a couple of years ago. This was when LIGO just got another upgrade, and they yet again did not see anything. And I was in the office of a quite renowned astrophysicist, cosmologist, and so on. And he explained to me why, of course, they wouldn't see anything because there's nothing to see, and explained to me in great detail why all of these efforts, which was completely useless. And now, looking at our little workshop, actually what I see is an incredible increase, an overwhelmingly increase of precision in experiments and theoretical efforts. And I'm not sure whether next time we meet for the third version of the Laboratory Cosmology workshop, we will have seen any new physics. But definitely the motivation for many of the experiments we saw was to basically improve on measurements of curves of existing physics. And that alone is a good motivation. It would be so great that if in a couple of years from now, some of the experiments, be it the tabletop experiments or the ones that improve precision on the exoplanet search on a more larger scale, actually will lead to something that we have not expected. So, and I think it was a great experience to see all of these different viewpoints getting together. Now we depart, we'll collaborate and read about each other, and 3 years from now, Hossein? Okay, very good. So get back to the lab and bring something to us in 3 years from now. So thanks everyone for coming, and I hope you enjoyed it as much as I did.
Thank you.